In this video, we'll make a circuit where the input is a DC voltage and the output is a square wave. For this, we will use an op-amp in the saturation mode. In most situations, when we're using op-amp in a saturation mode, we use a positive feedback as opposed to the negative feedback we've seen so far. So let's build a simple positive feedback circuit which will generate a square wave. Note that the virtual short assumption that the voltage between the inverting and the non-inverting pin is 0 will only be true when the op-amp is not in saturation. Therefore, we cannot make that assumption in this case. However, we can still make the assumption that the current going into the inverting and the non-inverting pins is 0. To begin the analysis, let's assume that the output is initially at plus V, which means it is in saturation, and the capacitor is discharged. We should keep in mind about this initial condition assumption and later make sure that the result of the analysis is independent of this assumption. Okay, since the output is at plus V, using the voltage divider rule, the voltage at the non-inverting pin will be V over 2. If the resistors R1 and R2 are not equal, then this voltage will be determined according to the actual values. Now let's see what is happening at the negative feedback side of the circuit. Since the output is at plus V, the capacitor begins to charge through this RC circuit until the charge of the capacitor goes slightly above V over 2. At this point, the voltage at the inverting pin will be greater than that at the non-inverting pin, causing the output to flip to minus V and the output at the non-inverting pin to minus V over 2. Since the output is now at minus V, which is less than the voltage at the capacitor, it will start discharging. Again, this discharge will occur until the charge at the capacitor goes below minus V over 2, at which point the voltage at the non-inverting pin will be greater than that at the inverting pin, causing the voltage to flip back to V. The whole sequence repeats again, giving rise to square wave at the output. Now, about the assumption we made at the beginning, we assumed that the output is at plus V and the capacitor is discharged. Pause the video here and repeat the analysis with some other assumptions. You can try different combinations of output and the capacitor voltages. If you don't end up with a square wave, that will be new, and let's discuss that in the class. Having said that, there is one alternative non-stable equilibrium for the circuit, and that is 0 voltage at the output and 0 voltage across the capacitor. As long as you can maintain these voltages, the circuit can stay in 0 output voltage. But in practice, there's always noise which will disturb the equilibrium. Let's also take a moment to discuss the assumptions we are making in our regular analysis of op-amps. Notice that the voltage at the inverting and the non-inverting pins are almost always different, which means we no longer have a virtual short. This is an important point we should keep in mind when analyzing op-amp circuits. In most cases, they are operated in the linear, non-saturation region, and the virtual short assumption is valid, but not in cases such as this. Yep.